Bismillah ar-Rahman ar-Rahim. This is Steel Structures class delivered by Dr. Qusay Al-Kaseasbeh from Mutah University. Today, inshallah, we're going to start with chapter 3, tension members. So what are the tension members? Tension members are structural elements that are subjected to axial tensile force, as you do see here. Okay, so if we do have a structural member, let's say we do have this structural member. So if we apply a tension force, okay, perpendicular to the cross section of this structural member, we can call this as a tension member. Okay. And in details, we will, let's say, study the tension members in this chapter, how to design it, how to check it, how to take out the whole, let's say, effect. So let's move down and see how we do that. So where we do, let's say, use the tension members. Actually, we can use the tension members, let's say, in bracing for building and bridges, or we can use them in cables for, let's say, suspended roofs system. So these are some of the examples where we do use the, let's say, tension members. So there is one thing here. The stress in an axially loaded tension members is given by, let's say, here is the stress, which is, or we can make it sigma, which is the force P dividing by the cross-sectional area. So that's what we call it, axial stress. Okay, it's different from, or let's say, yeah, from the bending stress. Okay, so here P is the load magnitude. Okay, this is load magnitude. Okay, and A is the cross-sectional area, or let's say the area normal to the load. Once again, if this is a structural member or tension member, so here is, let's say, P, which is the force magnitude, and here is the area, which is the area perpendicular to the load. Okay, what we call it a cross-sectional area. Okay, cross-sectional area. Actually, the existence or the presence of holes in a tension member, for sure, it will affect the stress at the cross-section through the holes. So let's move down and see what does this mean. In this example, guys, if you look at this figure here, let's work on this. So this is a gusset plate. Let me hash it here with the green. So this is a gusset plate. What does gusset plate mean? Here, this is what we call it. Gusset plate. And the gusset plate is a connection member to transfer the load to a support or to another structural member. Okay, so it's a connection member. It's not our mere interest here, but it's why not? Let's know what does it mean. It's a let's say a connection member to transfer. So this is the main job, to transfer the load to a support. Okay, or to another structural member. Okay, so الجاست بليت هي عبارة عن let's say a connection member أو عضو توصيل حتى تنقل اللود من structural member ل support أو من structural member to another structural member. Okay. In our case here, this is the tension member. I'm gonna hash it with red. Okay, so this is the let's say tension structural member. Why is tension? Because we do have a force here. It's away from the cross section, so that's what we call it here. It's a tension force. Okay, right now, if we pick a different color here and take a section here, okay, a cross sectional or a section here. So, and this is a section AA. If you see, this is the section AA, okay? Because if you take a section here, either you can look at it from down here. Yeah, let's look at it from down here. So this is the section AA. So this is the 1/8 inch. Why this is 1/8 inch? Because it's mentioned here. This is a bar 8 by 1/2. 8 is the width, which is this distance, and 1/2 is the if we deal this, so it's going to be this this distance, which is here, guys. So this is the 1/8 inch or 8 inch, and this is the thickness. Okay, so if you look here, guys, we do have, it's a solid section, yani we do have no holes. Okay, solid sections. So the area here, if we deal with the area here, or the gross area, we call the gross area, guys, because we have no holes. نسميها gross area. So it's going to be the width times the thickness. Okay, the width is 1/8 inch times 1/2. So the area here for section AA is 4 inch square. Okay, what if we take the section, let's say here, BB. If you notice here, guys, to make a connection between the gust plate here and the tension member here, we have either to bolt it or weld it. يعني ممكن بالبراغي أو بالحام. هون it's bolted. Okay, so here we do have bolts. Bolts اللي هم البراغي. So here, if you notice, we do have holes. So one thing here, so this is the cross section from the tension. Okay, this one here. This is the tension member. tension member زي ما حكينا هو العضو اللي خاضع لقوة tension. Okay, أو شد. And this is the gust plate. Okay, right now if you notice, our main interest, guys, here is to deal with this, which is the tension member, not the gust plate in this chapter. But in general, in the steel, you have to design both. Okay, so right now, if you see here, these holes are 7/8 inch diameter holes. Okay, high holes. So all the time we have holes and we do have bolts. Okay, so الهولز هم الفوهة أو الفجوة حتى نوضع فيها البولز، والبولز هو نفسه دائما هون عندنا. So this is 7/8 diameter holes. خليك منتبه إنهم holes. So here are the holes, which is this one and this one. Exactly, this is the first one here. This is the second. So this is the first. This is the second. And this is the holes go through both tension member والgust plate يعني تعدى من two members. Okay, so this is the gust plate. So right now, what is the area for the section BB? Okay. Here, let's put down the area. So the net area at the section AA, or sorry, BB, is equal the gross area minus area holes. The gross area, as we did calculate it here, it's equal the width times the thickness minus how many holes we do have in this section, we do have two, 1, 2. So this is 2 holes, okay? So how much the diameter for these is 7/8 inch, and the thickness is 1/2, is the same, okay? So in this area, you will see that the area is 3.13 inch square at the section, let's say BB. For the section AA, we have 4. So look at this, guys. If we have holes, for sure we will have less area. And if we have less area from this, let's say, stress equal P over area. So if area is less, means more stress. Okay, so we're gonna have more stress. In this case, at the section BB, we will have more stress than what we do have in section AA, because the area is, let's say, less. In this section, we will see how to, let's say, calculate the tensile strength for tension member. In general, tension members might fail by reaching one of these 2 limit states. The first one, excessive deformation or fracture, okay? So how to prevent the excessive deformation? All the time, let's say the load in the cross section should be less than, or let's say the stress generated by the load in the cross section should be less than the yield stress, okay? So for excessive, let's say, deformation, طبعا لما نحكي excessive deformation here نحكي عن yielding, okay? So the stress in case of, let's say, excessive deformation, أو خلينا نحكيها نسميها yielding, okay, it should be less than Fy, okay? For, let's say, fracture, this stress should be less than the ultimate stress. We will explain that soon, okay? So the nominal strength in the case of yielding, that's what we are looking for. And guys, we do have difference here. This is the stress. So if we call F dividing by, let's say, A, this is stress. If the load dividing by the cross-section area, this is stress. So this is a stress. And if we need to find the force, so the force is going to be the stress times area. This is just on the, I want to just let you or refresh your mind with these things. I know it's very simple to you or for you. Okay, so the nominal strength in the yielding is going to be, as I told you, P over gross area. It should be less than or equal yield stress. Just rearranging this one. So the P, and let's call this Pn, which is the nominal strength, is equal the yielding stress times the gross area. And this is very important. This is the nominal strength in the limit state of yielding, okay? In the case of fracture, the nominal strength is equal, as I told you, nominal is, and this is going to be the effective net area, which will be studied in the next few, let's say, sections. And it should be less than or equal ultimate stress. So the nominal strength here is equal, let's say, the ultimate stress times the E effective. And E effective all the time should be either equal to the net area or smaller. Net area, which is En, is equal A gross minus A holes. Okay, and then we will get the effective net area, which is U times En. We will study this and show you how to get it. Okay, the gross area which is the section AA in our previous example اللي هو section ما في يعني solid section we do have no holes ما عنده أي holes فيه. الholes هون it's easy to get the holes but all the time make sure that you are taking the diameter for the holes not for the bolt, okay, and we will study this in details later. So right now, since we do have two design philosophies, LRFD and ASD, so let's like go through them in details. In LRFD method, if you remember guys, the required load or factor load should be less than the design, let's say, strength. The design strength, which is phi and sub T. T here is, let's say, stands for tension, and this is the nominal strength. So here, PU is supposed to be less than or equal phi T times, let's say, nominal strength. Okay, and here, guys, if you remember, P sub U is the governing combination of factored loads. If تتذكروا, we do have load cases. Okay. Case number 1, case number 2, and so on. And right now you have to pick the largest, let's say, factored loads. يعني الأكبر قيمة وتعمل comparison مع design strength. And if you remember, for yielding, we take the phi is 0.9, and for a fracture we are taking it 0.75. And I told you why we are just taking 75 of the strength, because here the, let's say, the failure, let's say, mode in the case of fracture is very critical and severe than what we do have in here. يعني بهاي الحالة يا شباب احنا عندنا ممكن التنشن ممبرز يصير له failure بالييلدينج أو بالفراكشر بس. اوكي، فبهاي الحالة بالييلدينج بناخذ الفي is equal 0.9، الفراكشر بناخذها 0.75 من السترينث. فكأنه هون احنا بنقارن الفاكتورد لودز، يعني قديش السكشن عليه لود، وراح نحل اكزامبلز ان شاء الله ونقارنه بالديزاين سترينث للسكشن واللي هو ممكن نوجده من هاي العلاقه باستخدام هاي الفاكتورز. طبعا we mentioned that the nominal strength for yielding انه دائما هي Fy times gross area times P for yielding, which is 0.9. Okay, so we can use this directly. لازم we have to meet this condition, okay, or this condition must be satisfied. لازم نحقق هذا الcondition حتى to be safe, or let's say to say we are safe. Okay, for let's say fracture, we mentioned that the nominal strength is ultimate strength, which is Fu times the effective net area, and times phi, which is 0.75 in the case of fracture. So we can use this to check the fracture limit state. Okay, so this is in case of, let's say, LRFD method. Okay, and right now, which one we should pick is the yielding or the fracture? The smallest one is going to be the design strength here. Okay, so the smallest one is the design strength or tension member design strength. يعني الأقل في هاي القيمتين هم راح يكونوا design strength واللي راح نصمم عليه. So here the smaller of these is the design strength of the member. So this is very important because you have to tell which one is the control. لازم يتحدد. For ASD, which is allowable strength design, all the time the required, let's say, strength or the applied load, here it's applied surface load. Okay, applied surface load means, okay, loads means we do have no factor, or the required force should be less than the nominal strength dividing by the safety factor or equal. Okay, here is the definition for all these factors here. For yielding, safety factor is equal 1.67. Okay, and in this case, guys, let's say here, if we say P or nominal strength dividing by safety factor, and nominal strength for the yielding is going to be the yield stress times the gross area. Okay. make it nicer here. So this is a gross area dividing by, let's say, safety factor, which is 1.67 in the case of the yielding. So, okay, this is for yielding. Okay, in the case of fracture, and if you just divide 1 dividing 1.7667, you will see that this one is going to be 0.6 Fy gross area. Okay, in the fracture, same thing here, which is Pn dividing by safety factor in the case of fracture. So Pn, or the nominal strength here, is equal F, or ultimate strength, times effective net area, dividing by 2, because the safety factor in the case of fracture is equal to, so this one is going to be 0.5 Fu times AE. Okay, so these are the two limit states in the case of ASD method. Okay, in this example, which is example 3.1, we will, let's say, check the design strength, or let's say, find the design strength for the tension member using either, or let's say, both LRFD method and ASD method. So the problem statement says 1/2 by 5 plate. It's a rectangular plate, which is 5 is the width, 1/2 is the thickness of A36 steel. So it's this is, let's say, the most common steel type is used as a tension member. So here it tells you that it's a tension member. So it's connected to a gust plate. Okay, here if you see here, guys, this is the gust plate. Okay, so this is gust plate with 4 5/8" diameter bolts as shown in this figure. So here, the tension member, which is this one, I'm gonna highlight it with the green. This is a tension member, okay, bolted to the gust plate with 4 5/8" diameter bolts. Okay, and make sure here they are telling this diameter for the bolts, is not for the holes, and I'll show you how to calculate it for the holes. Okay, and right now, why we call this tension? Because it's subjected to a tension force here, and this one, as it's mentioned here, it's 5 by 1/2 or 1/2 by 5. So in this case, this is the width, which is the 5 inch, and the thickness is 1/2. The length, we don't care about the length, okay? So here it tells you to assume that the effective net area, which is A sub E, equal to the actual net area, okay? We will cover the computation for the effective net area in the next section, okay? So here's one thing to assume. Effective net area, which is A sub E, is equal to the net area. In the reality, effective net area is equal U times net area. Here, in this case, we assume this is equal 1. Okay, so what is the design strength? So we need the design strength, which is nominal strength times the phi for LRFD method in A, and in B, we need to find the allowable strength for ASD method, which is same as a design strength, okay? The same concept, but then with a different way how to calculate it. Before we going further, if we take a section here, okay, and let's call this AA section. For sure, we're gonna have 2 holes in this section. Why we are not taking it here, let's say, or somewhere else without holes? Because all the time we should design based on the worst scenario. لازم نصمم على the worst scenario. مش ناخذ the safest cases، ناخذ the severest cases، الكيسز الأخطر. اوكي، فبهاي الحالة هو ممكن إذا عملنا section من هون أو حتى من هون، بالأخير we do have 2 holes. And if you look to this from the side, you will see this is the solid area. okay, and we do have holes here. If we call this hole 1, this is hole 2, so this is going to be hole 1, this is hole 2. The thickness for this is 1/2, as we, or it's mentioned here and here. And right now, let's say the diameter for the bolt was 5/8, okay? Diameter for the bolt is equal, or let's say, yeah, equal the diameter for the holes plus 1/8. يعني دائما هاي ال 1/8 هي, or let's say here minus. So minus. يعني if this is the hole, okay, and we do have a bolt here, so the diameter for the bolt, okay, or let's say for the holes, is equal the diameter for the bolts, okay, plus 1/8. دائما بنزيد 1/8 لقطر البولت, okay. It's much better saying it in this way, okay. So right now, this is how much the diameter for this hole is going to be. The diameter for the bolt, which is mentioned here, plus 1/8 وهي ثابتة طبعا. Sometimes in the manual they are using 1/16, but just take 1/8. So if you add these together, you will get the diameter for the holes. This is the diameter for the holes, or the hole is equal 3/4. Okay, let's move down and see how to solve this example. Okay. For yielding right now, let's calculate, let's say, the nominal strength. The nominal strength for yielding is equal yield stress times the gross area. Okay, yield stress, it's given to us A36, so the yield stress is 36 KSI. So this is going to be 36 KSI. Okay, the gross area here, it's going to be the width times the 1/2, which is the thickness. So it's going to be 5 multiplied by 1/2, which is the thickness. هاي اللي هي width of the plate وهذا thickness. Okay, so in this case we're going to have nominal strength طبعا based on yielding. Okay, ولازم تكون ميزت انها للييلدينج، لانه احنا هون بنستخدم الييلد ستريس وبنستخدم الجروس اريا. So this is going to be 90 kips. Okay, ال FY, let's say the yield stress is 36 KSI, kip per inch square. The nominal strength, which is a force here, it's 90 kips. Okay. Okay, this is for yielding. If right now, let's move with the fracture and keep LRFT method and AFC method for data. For a fracture, the nominal strength is equal, this is nominal strength, not the design strength, is equal F, or ultimate stress, times effective net area. Right now we need to call or to calculate the net area. The net area here is going to be the gross area minus area holes. Okay, gross area, we know it here. It's 5 by 1/2 minus how many holes we do have in this section? Two holes times what is the thickness is 1/2. What is the let's say hole diameter is 3/4, as we did calculate it. Using this, you will get that the let's say if net area is 1.75 inch square. Okay, sometimes we will do this as an inch square. Okay, and as mentioned or assumed in the text, in the let's say problem statement, the effective net area is equal net area, so which is equal 1.75 inch square. And right now the nominal strength is equal, Fy for the steel A36 is 58, and that should be given to you in the question. So this is 58 times 1.75, and this one is equal 100 let's say, or 1.5 kips. And kips because these are strength, forces, loads. Okay. And right now, if we need to use either LRFD method for yielding and for fracture. So LRFD method, let's take it for yielding, which is equal phi times nominal. If you take here, you will see that for yielding, the nominal strength is equal 90 kips. Okay. For fracture is equal 1 or 1.5 kips. So in this case, for yielding, in the case of LRFD method, phi is equal 0.9. Okay, times the nominal strength based on yielding 90. So this one here is equal 81 kips. This is the design strength based on yielding limit state using LRFD method. Okay. And right now, if we do that for a fracture, okay, for a fracture, phi is equal 0.75 times the fracture nominal strength, which is 101.5, and this one here is equal to, let's say, 76.1 kip. So for LRFD method, which one is the design strength? Which one we should pick? For sure, we will pick the smallest one, which is based on the fracture. So the design strength here, if we tell the design strength for LRFD method is equal, خلينا نقول 76.1 كيب. فلازم اللود اللي بدك تحمله يكون أقل من 76.1 كيب أو يساوي. Okay, so what about, let's say here for LRFD, ASD method, okay, B, ASD method, or let's say use ASD method. If you remember, guys, based on yielding, the allowable strength is equal, and here we can, let's say here I want to make it much nicer. Okay, it's going to be nominal strength dividing by safety factor for yielding. Nominal strength based on yielding, the same one here, it's same, بيشبهوا بعض مش غيره. Dividing by 1.67, so this much is equal 53.9 kip. And for fracture, this one is equal, the one here, which is 101.5 dividing by 2, and this one is going to be 50.8 kip. And which one is the control? Is this one, the fracture. So the design strength based on ASD method is 50.8. طبعا شباب بهاي الحالة just to sum up، أول إشي بنوجد nominal strength based يعني nominal strength هون based on yielding based on the fracture. Okay, based on yielding is very easy اللي هو yield stress times gross area, and we will get this one. For fracture, we have to get the effective area. In this question, it's assumed to be the net area. So the net area is gross area minus area holes. So we need to come up with this area. Multiply it by the ultimate strength, you will get the nominal strength based on fracture. Okay, so up to now, everything is same. Okay, right now, if you have been asked to find it for LRFD method, so you have to use different, let's say, factors, which is 0.9 here, 0.75 here, and make a comparison if that was let's say a requirement. لازم تقارنه بالload combinations for the LRT method. For AST method, yielding it's going to be same nominal strength based on yielding and fracture. This will be the difference here, just the safety factors. By this, you find the design strength for the tension member based on LRT method and AST method easily. Let's solve another example, which is example 3.2. And the problem statement says a single angle tension member. Okay, this is the angle. So this is single angle tension member, which is L 3.5 by 3.5 by 3/8. This is actually equal leg angle. Okay, if you see this, this is the angle, and it's said, or it has been said that single angle because sometimes we have double angle. It's not to scale. Here, this one 3.5 inch, 3.5 inch, and the thickness for both legs is equal 3/8 inch. Okay, so this is the cross section for angle. Okay, this is the cross section for this angle. Is connected to a gusset plate. So this is the gusset plate here. Okay. With let's say 7/8 inch diameter bolts. So this diameter for the bolts, for the holes, diameter is equal 7/8 plus 1/8. Okay, so which is equal 1 inch. All the time, make sure that you are using the correct diameter. As shown in the figure, A36 steel is used. The surface loads are, okay, so the dead load here is equal 35 kip, okay, and the live load is equal 15 kips. So surface loads mean unfactored loads. يعني هون إذا بدنا نستخدم LRT method بدنا نعمل لهم factor. Investigate this member for compliance with the AISC specs, and we have to assume that the effective net area, which is AE, is equal 85% of the net area. Okay. الآن هون هذا اللود المطبق على هذا التنشن ممبر وهذا التنشن ممبر، معناه بدنا نحسب الديزاين سترينث لهذا التنشن ممبر ونقارنها بالفاكتورد لود بالكيس الRFD method وبالسيرفيس لود combinations, the crowd load cases for AST method. Let's clean up and start solving this example. First of the thing, we need to find the design strength, let's say for LRT method based on yielding, or let's say here LRT method and AST method. That means we need to find the nominal strength based on yielding, based on the fracture for both cases, LRT method and AST method. So here for yielding, for sure, the nominal strength is going to be, let's say for yielding, it's going to be yield stress times gross area. Okay, how to get the gross area for this, let's say angle? Let me show you how to get it from the manual. But here, remember that the yield stress is 36 because we are using A36 steel, and the gross area, it's 2.5 inch square. How we get this? And this one, we will get it from the part 1 in the manual. Let me show you how to get it. Okay? If you go to the steel manual, the one I just uploaded to you in the files, you will go to the part 1, which is dimensions and properties, table 1.7. Okay, this is table 1.7 here. Okay, table 1.7, angles, properties. Okay, if you scroll down here, you will, and we have to find L 3.5 by 3.5 by 3/8. Okay, this is our let's say angle. So this is 3.5 by 3.5, but the thickness is by 3/8. And just a minute here, let me just scroll down a little bit. Okay, so here once again 3.5 by 3.5 by 3/8, and the area here, which is in inch square, if you go this way, you will see that the area is 2.5 inch square. Okay, 2.5 inch square, and by this you can get the area. Let's say we do have many things here to think. Let's say moment of inertia, let's say elastic suction modulus, radius of gyration. There are many factors. We will use some of them later in this class. Okay, so by this we got the gross sectional area. This is A gross, okay, for this section, which is equal to 2.5 inch square. And let's get back to our example. Okay, so once again, the nominal strength based on yielding is going to be yield stress, which is 36 times 2.5, which is the cross-sectional area from the manual, and this one is equal 90 kips. Okay, right now, okay, for the fracture, this is for yielding once again. Okay, for a fracture, the nominal strength is going to be the yield stress, which is given to us 58 times the effective net area. So how to find the effective net area? In this example, it has been mentioned that it's 0.85 net area. So the net area is equal the gross area, which is 2.5, minus how many holes we do have. It's one hole, okay? It's 1 times the thickness for this one is 3/8 times the diameter for the hole, which is 7/8 is the diameter for the bolt, plus 1/8. So in this case, the net area is equal to 2.125 inch square. So the effective net area is going to be 0.85 times this much, which is 2.125, and this one is equal 1.806 inch squared. So this is the effective net area, this is the net area, and this one is the gross area. So the nominal strength is going to be 58 times this much, which is 104.7 kip. Okay, so right now we found the nominal strength based on yielding and fracture. So right now, okay, let's use LRFD method and AST method. For LRFD method, the design strength based on yielding is going to be phi times the nominal strength. Nominal strength, we got it from here, and the phi is 0.9, so it's going to be 81 kip. For fracture, it's going to be 0.7 times, here is the nominal strength based on fracture, which is 78.5. Which one is the smallest? So this is one. This one is going to be the control. So this one is the design strength based on LRFD method. And by the way, guys, you don't need to use both methods for design. يعني مو شرط تستخدم two design philosophies, LRFD method و AST. ممكن تستخدم واحدة منهم, but as I mentioned earlier in this class, LRFD method is the newest one. AST method was in the 70s. But أنت دايما تستخدم. In this class is different. You're gonna use what I'm asking you for, but in general in your life, or let's say future life, you can use either of these methods. So, but we are not done yet. Okay, so this is the design strength. Right now we have to make a comparison between the design strength and the applied load. So the applied load is mentioned that the dead load is 35 kips, the live load is 15 kips. If we are going through the, let's say, load combinations, 1, 2, 3, and so on for LRFD method. An example, let me just clean this and move down a little bit. Okay, so here, if we are using the first combination, so it's 1.5 dead load. So here 1.4 times 35, this is the dead load, it's given to us, 49. Combination number two, 1.2 times 35 as a dead load plus 1.6 times the live load 15. So this is going to be 16 kips, and you have to try all the load combinations as تعرفهم كلهم. But in this case, we know that this is going to be the control. Right now, what you have to do to make a comparison between this and the design strength. So the design strength is 78.5 kip as we just calculated. So for sure this one is less than the design strength. So اللود المطبق أقل من المحتمل أو ممكن يتحمله السكشن. So we are okay, or we can say the member is satisfactory. Okay. Okay, right now let's go through the ASD method, because in part B it's mentioned that let's use ASD method. Similarly, guys, the nominal strength for the yielding, here sometimes they call it cross section, but they mean yielding. So it's going to be the nominal strength, or the one we just calculated, dividing by 1.67, which is the safety factor for yielding. So this is going to be 53.9 kips. For net section, or let's say fracture, the nominal strength based on a fracture, which is 104, dividing by 2 as a safety factor for a fracture, and this one is going to be 52.4 kip. Which one is going to be control? For sure, this one for fracture. So this is going to be the control, and we have to make a comparison between this and, let's say, right now, same. We need to let's say check all the load combination, but for ASD method, not this one, مش هذولا ASD method. We will see that the case number 2 is equal dead load plus live load, which is equal 35 plus 50, and this one is 50 kip. Okay, so here the applied load, which is 50, sorry, is less than the design strength, which is 52.4. So the section is satisfactory, or the member is satisfactory, and the section is safe and okay. Okay, so by this we did solve, let's say, or find the design strength for the angle and make a comparison between the applied load. Okay. I'm gonna stop here today, and please, if you do have questions, you can send me an email or chat with me on Microsoft Teams. Thank you.